Hello everyone, welcome to this particular module. In this particular lecture, we will mainly learn about the electrical supply system and AC and DC power supply scheme. So let us start. So the overall electrical power supply system, it basically consists of some process. What are those process? First, electrical power generation, then transmission of the power, then distribution of the power, then utilization of the power. So this entire chain of these electrical supply system, it is called a network. Okay, so the any electrical supply system, it has to follow this chain. Okay, so the electrical power is generated at the power stations from power plant. Then that power is transmitted through towers and conductors. Then that power is distributed at 11 kV using overhead conductors, and then finally that power is utilized using among the consumers and the load. So let us understand this electrical supply system. So electrical power, it is generated. I'm telling about the AC power here. So electrical AC power is generated at the power stations at 11 kilovolt. So why we are doing it at 11 kilovolt? Because if we generate the power at more than 11 kilovolt, there will be technical issues. So in India, we are restricting the power generation at the power stations at 11 kilovolt. Now in the power station, we have different power plants. We have hydropower plant, we have thermal power plant, we have nuclear power plants. So these power plants are used to generate the electrical AC power. Alright. Then that generated AC power is brought to a bus. What is bus? Bus is nothing but a junction or hub. It basically connects different lines or links in the electrical power supply system, and also it connects different electrical equipments. Okay, so when the generated power appears at bus, here it is decided where to transmit this generated power. Okay, now what 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 I'm supposed to do now, that 11 kV power, it is given to the step up transformer. Okay, so this step up transformer is located near to the power station. So we are stepping up the 11 kV generated voltage to the 400 kV. Now you can ask, like, why we need to step up this voltage from 11 kV to 400 kV. This is because, see, ultimately we need to transmit this power, and that power has to be used by the consumers. Okay, so, and this 11 kV generated power, I need to transmit over a long distance. If you want to transmit this power, let's say over 200 or 300 kilometer like distance, so by that time it reaches to the destination, like, you won't get that 11 kV. Okay, because you will be transmitting the power using some conductors or transmission line. So over this long distance, if we are transmitting this 11 kV power, it will suffer the, like, losses in the line or conductor. So due to that, by the time the power reaches to the destination, we won't get, only few volt will be left out. Okay, we know P equals to VI, right? Power equals to voltage into current. So for a given amount of power, if I am increasing the voltage V, then the current I has to reduce. if the current flowing through the conductor it is reducing, then what will happen? The loss, I square R loss in the conductor will also be reduced. Okay, so in order to reduce the loss in the transmission line or in the conductor through which I am going to transmit this 11 kV power over a long distance, I am stepping up this voltage to 400 kilovolt using the step up transformer. Alright, then these voltage it is transmitted using a transmission line. What is a transmission line? It can be a conductor or it can be a dielectric. Suppose you have a, at the input side you have a transmitter, and at the output side or receiver side you have an antenna. Okay, so from the transmitter, let's say it is generating a radio frequency signal. Now this radio frequency signal it is used to drive the antenna which is at the receiving side. Okay, so the connecting link between the transmitter and the receiving antenna is called the transmission line. Okay, so here using this transmission line I am just transmitting this 400 kV high voltage. So these are high voltage transmission lines. Okay, so transmission lines can be overhead transmission line or it can be underground cable. So usually in rural areas we use the overhead transmission line, and in city areas usually we use the underground cable. So what is this overhead transmission line? In this overhead transmission line, bare conductors are used. Bare conductors means we have simply the aluminium or copper conductors. Okay, so but they are not safe. That means if we accidentally touch them we can get the electrical shock. Okay, but in case of underground cables, what happens? The conductors are insulated using some non-conductive materials. It can be your some plastic, rubber, like this kind of material. So in that case, this insulation will prevent the electrical current flow where it is not required. Okay, so you won't get accidental electric shock if you touch the cable or conductor. Okay, and also it will protect the conductor from the short circuit. So here what I told, this transmission line can be either overhead or OH transmission line, or it can be underground cable. Okay, and this transmission here, this transmission is called the primary transmission. Okay, next what I need to do, this 400 kV voltage when it is reaching to a substation, this is my first substation. What is a substation? Substation is a facility that can control or manage the electric voltage level. Okay, so if you need to convert the voltage level, if you need to step up or step down the voltage, so in the substation we will be having the transformer, so that operation can be done here. Okay, so this 400 kV voltage I am stepping here in the first substation. I am stepping down this 400 kV voltage in this first substation using the step down transformer. So I am stepping down to 33 kilovolt. Okay, because ultimately for the consumer use I have to convert it to either 440 or 220 kV. Okay, so that is why I am stepping down this voltage at the first substation. Then there is a bus. So I already told this bus is nothing but a junction or hub in your substation which will connect different lines or links in the substation, or it will connect different electrical components. Okay, so here also we have another transmission line. So this transmission is called the secondary transmission. Okay, then again in the second substation we have another step down transformer. In the second substation, we are again down converting this 33 kV to the 11 kV. Then again there is a bus which is nothing but a junction or hub in the second substation, and this line again I have this transmission line here to transmit this 11 kV. So this transmission here is called the primary distribution. This transmission over here is called the primary distribution. Okay, so from here onwards my distribution of the electric power starts. Then this is my domestic transformer. Here what happens, that 11 kV is again down converted to 440 volt using a step down transformer. So again using the transmission line, it is going to our either some industry or some heavy load centers or our houses. Okay, so this 440 volt is usually given where we need this 440 volt is required in industries, okay, where you are running the heavy loads. This 440 volt is usually the three-phase system, three-phase four-wire system. So we have already seen this single-phase and three-phase system earlier. So in three-phase 440 volt system, we have three-phase wire and one neutral wire. And we know that in three-phase system, the phase shift between any two phases, they are 120 degree. Okay, so if you are measuring the voltage between any two phases in three-phase 440 volt system, it will be your 440 volt. Okay, and if you are measuring the voltage between one phase wire and one neutral wire, that will be your 220 volt. If I want to use the voltage in our household appliances and to run the fan, light, then I need the single phase 220 volt. Okay, single phase 220 volt means I need one phase wire and one neutral wire. So that is how finally this electricity which is generating at the power station, it is utilized by the consumers. Now you can tell that why, like here we understood that this 11 kV it is stepped up to 400 kV. Then why we need to down convert this 400 kV in so many steps? Why we can't down convert it in single step? Why we can't use a single step down transformer? Because if we want to step down this 400 kV to 440 volt, it is a huge conversion ratio. You can understand, right? 400 kilovolt to 440 volt. So that high amount of conversion ratio, like having a transformer with that high amount of conversion ratio, it is not practically feasible. That is why at each and every step we need to step down the 400 kilovolt voltage. All right. Next, so what we have discussed over here, that is an AC transmission system. Okay, we are generating the AC voltage and finally we are utilizing that AC voltage. Okay, but what if the transmission system is DC? When the power is transmitted by the DC, then there will be a lot of advantages if we compare with the AC transmission system. So what are these? Let us see. It is telling the amount of insulation which is required is less in DC transmission as compared to that for AC transmission. What do you mean by that? In DC transmission, when I tell 230 volt, that means that is a peak value or maximum value. But in AC transmission, when I tell 230 volt, that is what? That is my RMS value, RMS voltage. We know what is the relation between the RMS voltage and peak voltage. Vrms equals to Vm by root 2. Okay, so if 230 volt is my RMS value, what will be my peak voltage? Root 2 is 1.414. So that 230 multiplied by 1.414, so around 325 volts. So obviously in case of AC, that equivalent of 230 volt is 325 volt. 230 volt RMS means 325 volt peak voltage. Okay, and in case of, this is in case of the AC, but in case of DC, 230 volt is, that is my peak voltage or the maximum voltage. So obviously since the voltage is higher for AC, so we need the insulation in DC in less amount. Insulation where we are providing on the conductor, we are putting a protective coating on the conductor in order to have the safety, in order to protect our conductors from short circuit. So that insulation, the amount of insulation will be required less in DC transmission compared to the AC. Okay, now it is telling the size of towers, cross arms required are small for DC transmission system. So we all have seen these towers. These are long structures. Okay, and you can see these, with these towers we have the overhead transmission lines, they are suspended. Okay, now with these towers we have this horizontal component. Okay, we have this horizontal component which are called the cross arms. Okay, so these are attached to the towers, they are here to support the conductors and insulators. Okay, so in case of the DC transmission system, the amount of towers and cross arms required will be less. Okay, now if you use the DC transmission system, it will improve the stability of the system. Next advantage is power factor of the DC transmission system is unity. Why? Because in DC transmission system, the voltage and current, they are in phase. Okay, we don't have any concept of reactive power in DC. That means there is no concept of capacitive or inductive power. There is no phase difference in DC. So that cos phi term will be 0. Okay, that phi is, that cos phi term is 1 because phi is 0. We know cos 0 is 1. There is no phase difference in DC. There is no change in current, obvious. There is skein effect. Skein effect increases the effective resistance of the line conductors. So this skein effect is usually observed in AC, not in DC. Okay, so when that AC current flows to a conductor, that AC current is distributed non-uniformly throughout the conductor. Let's say this is a conductor, and when the AC current flows to the conductor, it is distributed non-uniformly throughout the conductor. You will find that at the edge or surface of the conductor, the current density is more compared to the inner side. Okay, this is called the skein effect. So due to this skein effect in AC transmission system, what happens? The resistance of the conductor increases. If the resistance increases, then the I square R loss in the conductor also increases. So but in DC, since the current in a conductor, it is distributed uniformly, we don't have that kind of problem. But DC or high voltage DC transmission, HVDC, they also have some disadvantages. What are there? There is no equipment like a transformer available for step up or step down the voltage. So these has to be done on the AC side only. Like first I need to convert the AC to DC in order to transmit the power using the high voltage DC transmission line. Then again at the receiver side, I need to convert the DC power back to AC. Okay, now why in transformers at the input side we give AC, why not DC? because when we give the AC power at the input side, at the primary winding of the transformer, we will have some alternating magnetic field. Okay. Now, due to the Faraday's law of electromagnetic induction, that due to that alternating magnetic field in the primary, some EMF will get induced in the secondary winding. Okay. But in case of DC system, that magnetic field that will be created in the prime, if you are giving some DC supply at the primary of the transformer, then it will create a steady magnetic field at the primary winding of your transformer. So in that case, no EMF will get induced in the secondary. That is why we are using the AC supply at the input of the transformer. Now, what is the second advantage of HVDC system? Power cannot be generated at high voltages because of the mechanical commutation problem. Okay. Now, there are limitations with HVDC switching devices and circuit measures also. The HVDC transmission system, it is more economical when the distance of the transmission line is more than 600 km for OH line or overhead line. Now, the capital cost of DC transmission system is higher when compared to that of the AC transmission system, when the length of the transmission line is less than 600 km and less when the length of the transmission line system is greater than 600 km. That means it is telling that when the distance, when the length of the transmission line is less than 600 km, it is always economical to go for AC transmission system, while when the length of the transmission line is more than 600 km, it is always convenient to go for DC transmission system. Now let us understand why. See, when the length of the transmission line is less than 600 km, then at this case what will happen? If the length of the transmission line, if it is less than 600 km, if you notice from this graph, y-axis, it is telling about the station cost, like and at the x-axis we have the transmission distance. Now, if you look at this DC transmission system, how this system works at the generator side or the power station, we have the AC power is getting generated or AC voltage is getting generated. Then that voltage, we know we had to step up the voltage. Then that voltage we need to give to the rectifier unit, which will convert that stepped up AC voltage to the DC voltage. Because here we are using the DC transmission system, I need to pass the DC voltage to this through this DC transmission line, HVDC, high voltage DC transmission line. Okay, that is why I need to convert this stepped up AC voltage to the DC voltage. So that DC voltage will be easily transmitting through this HVDC transmission line, and at the receiver side I need to have an inverter circuit because I need to convert the DC voltage back to the AC voltage, and that AC voltage needs to be stepped down using a step down transformer, and then it will be distributed and utilized. Okay, now why we are using this, why we are preferring the AC transmission system for less than 600 kilometer length of transmission line? This is because you can see at the sending side and at the receiving side. At the sending side we have a rectifier unit, and the receiving side we have an inverter unit. So these are the part, this rectifier unit and the inverter unit, these are the part of the converter stations. Okay, so in the converter stations at the sending side and the receiving side, we have the complex power electronic components like IGBT or insulated gate bipolar transistor and your SCR. Okay, so that is why due to these costly converter stations at the sending side and the receiving side, the cost becomes very high if we are using the DC transmission system when the length of the transmission line is less than 600 kilometer. So for those cases it is always economical to use the AC transmission system. But when the transmission line length is greater than 600 kilometer, then what will happen? See, when you are transmitting electricity in terms of AC, the AC is like continuously changing the polarity, right? So if you are transmitting the electricity in terms of AC at high voltage, then in that case the energy lost as heat will be more. Okay, you will be needing more number of conductors. But in case of the DC transmission system, since the direction of the current is constant, so you if you want to transmit the electricity using the DC system at very high voltage, the energy lost will be less. So we need less number of conductors to transmit the electrical power. Okay, so in terms of the number of conductors and energy loss, we can make it economical, even though here also we will be having like costly converter stations. But when the transmission line length is more than 600 kilometer, at least in terms of energy loss and number of conductors, we can save the cost. This is the reason. So here in the y-axis we have the station cost and x-axis we have the transmission distance. So as I told, when the length is less than 600 kilometer, we have to, this AC represents the orange line, we have to go for AC. Okay, for more economic. And at 600 kilometer, you can see this point is called the break-even point. At 600 kilometer, like the cost for AC and DC will be equal, and when we go beyond 600 kilometer, it is always economical to go for DC transmission system. Next is we need to know different types of like DC transmission link. That means this HVDC transmission line we have seen here, right? So now we will see different types of HVDC transmission line. So before we start that, we need to understand one effect which is called corona effect in transmission lines. What is that? Suppose if you have a conductor, in the conductors what we have free electrons. Okay, and this conductor is surrounded by air. Okay, and air we know it is dielectric, but it is not a perfect dielectric, because in air we have the free electrons, we have the ionized particles, right? Now if you increase the voltage across the conductor, what will happen? When the voltage it crosses some critical value, huge amount of temperature will be generated inside this conductor. As a result, like outside we have air, right? This conductor, it is surrounded by air, so these air particles will also get ionized. Okay, once this air particle is also ionized, see, current will start to flow. Current always it try to find out the low resistance path. So once these air molecules are also ionized, the current from the conductor will start leaking. Okay, so along with like flowing through the conductor, it will also start flowing through the air. Okay, so as a result, you will be observing some violet color like electric discharge. That is called the corona discharge. That is why sometimes if you are standing nearby that overhead transmission line, sometimes you can hear some hissing sound. That is because of the corona discharge. So due to that high voltage, some high electric field is generated, like which is surrounding the conductor. So due to this high electric field, when it is comes in contact with the air particles are ionized, and that is how we observe that discharge or that hissing sound. And when that corona discharge happens, that ozone gas is emitted. Okay, so this is the corona effect in the transmission line. Now we will learn about different kind of transmission line, or we can also call it link. First one is a monopolar link. So what monopolar means? It is the transmission line, it is having only one polarity. So here in the generating station, AC power is getting generated, then that AC power is getting stepped up here using the step up transformer. Then that stepped up AC power is given to the rectifier circuit to convert it to the DC power or DC voltage, so that we can easily transmit that DC voltage through the DC transmission line. And at the receiver end we will be having the inverter to convert that DC back to AC, and that AC voltage will be again stepped down using a step down transformer, and it will be distributed and utilized. Okay. Now here the DC transmission line that we are using, it is a negative polarity conductor. Okay, negative polarity conductor means in conductor we know we have the free electrons. When there are excess number of free electrons are there in the conductor, we will call it the negative polarity conductor. Now if like some electrons are removed, some free electrons are removed from the conductor, it will become a positive conductor. Okay, now we have previously discussed this corona effect, right? So if we are using the negative conductor or negative transmission line, the corona effect will be less. Why? See, I told when I am applying a high voltage, an electric field will get created surrounding this conductor. So this intensity of the electric field, it will depend upon the polarity of the charge carrier. If it is a positive charge carrier, if it is a positive conductor, or if the charge carrier is positive, the direction of the electric field will be outside. Okay. If it is a positive conductor, then what will happen? In case of a positive conductor, a strong electric field will be created, okay, at different points surrounding the conductor. So in that case, the corona effect will be more. Okay, it will ionize this neutral air particle surrounding it more. Corona effect will be more. Corona effect is one kind of loss, right? We don't want any kind of loss during our transmission. But if you have the negative conductor, or if you have a negative charged particle, then in that case the electric field won't be that much strong, okay, at surrounding the conductor. Okay, so if that electric field is not that much strong, in that case the corona effect will be less. So here, why we are calling it monopolar? Because we are only using one polarity transmission line, and that is the negative polarity conductor, in order to reduce the corona effect. But somehow, let's say there is some fault in the transmission line, then entire system is useless. Okay, so that is the drawback of this monopolar DC link. Next, coming to the bipolar link. In the bipolar link, what we have? We have the AC system. So that AC power will be stepped up using the step up transformer. Then that power will be converted to the AC power, will be converted to the DC power. It will be transmitted through the DC transmission line. In the receiver side, we have inverter. It will convert that DC power back to AC, and finally it will be stepped down to make it usable for the user, like consumers. Okay, so as you can see here, we are using the two transmission line. One is the positive conductor, positive polarity conductor, another one is a negative polarity conductor. So here this first conductor, it is used for the transmission of this DC voltage, and it will be given to the inverter. And the second transmission line, it works as the return path. Okay, and you can see at the center of both these converter station we have the earthing. So what is the advantage of using these two DC transmission lines? In case one some fault occurs at one transmission line, entire system won't get become useless because another transmission line will be active. Okay, so in that case, suppose this transmission line is at fault, but this transmission line is working. So in that case, the earth will provide the return path. Okay, so here this conductor is the positive polarity conductor, and here it is the negative polarity conductor. So due to the positive polarity conductor, corona effect will be more, but due to the negative polarity conductor, corona effect will be less. Next we have the homopolar link. In the homopolar link also we are using the two transmission lines. So but here both the transmission lines, they are negative polarity. So both will contribute to reduce the corona loss. So first transmission line is to transmit this DC voltage to this receiving side, and second transmission line is there why, to provide the return path. And here also at the center of the converting stations we have the earthing. In case one transmission line is at fault, we can use the second transmission line. So this homopolar link is a most effective, because here we are using two negative DC transmission lines. Okay, so which will greatly contribute in reducing the corona effect. Rest of the systems are same. Here we have the AC power. We will be stepping up the AC power using the transmitter. We will give it to the rectifier to convert it to DC. Then it will be transmitted through the DC transmission line. Again that DC will be converted to AC using the inverter. Then that AC will be stepped down using this step down transformer to make it usable for the that consumers.